session of short talks, and then the remainder of the workshop today will be some working group sessions for the invited participants of the workshop. So I'll go ahead and pass things to you, Nati.
Okay, thank you. So this appears in the schedule as a survey. I should maybe start by a disclaimer that this is far from a comprehensive survey. In particular, there's been tons of work in the past few years about improvements in methods and analysis, and I'm not going to survey that. I think that'll be an interest in fairly limited audience here, and more my intent is to focus not on the answers, but rather the questions, and to give a bit more of a historical perspective. So as you see, I'll start with work from actually over 10 years now on distributed learning. We'll see how it aligns kind of with how we think of it now, and then spend also some time talking about a particular analysis framework, again, trying to highlight more its deficiencies rather than its strength. And I should say that this is, I asked some people to, what they think is important that I cover. Nina and Peter, who's here, Servit, Ling Shao, and Kshitij. But what I say is entirely kind of my biased view. I'm not like, you shouldn't take this as representing these people, from which maybe I got some ideas, but I didn't also actually follow their suggestions, and definitely I'm solely responsible for this. I will show quite a bit. I think Nina, unfortunately, couldn't be here, and you'll see how there's like I do want to highlight some of her work, so we'll see that. And also, I should say this is based on work with other people. Mostly, I want to highlight Blake. That really, at least my work that I will present is actually not my work. It's really Blake's work that I was lucky enough to be involved in. Okay, let's start. So we're talking about, I think, I'm not sure actually what Ginger said, the distributed, you say distributed, this is federated learning or federated optimization? Okay, so I mean, I wanted to start by getting out of the way that there's no, from my mind, there's absolutely no distinction in learning and optimization, just synonyms for the same thing. So just make sure everybody is on the same page here. The type of problems we're going to be thinking of is stochastic optimization problem. I'll be talking only about these stochastic optimization problems. We want to minimize some population objective, which is defined in terms of an expectation with respect to some unknown source distribution D of some instantaneous subjective F. And we want to do that just based on sample access to D. Okay, so this is a general formulation. I mean, maybe you want to think particularly on supervised learning, where your source distribution, your randomness Z is pairs of like example and label. And maybe you're also used to thinking of your optimization variable not as X, maybe X you think of as the example, and you're used to thinking of your optimization variable as W. I know the weights of your network. This is a special case covered by the more general formulation, of course, included in supervised learning. And if you are used to thinking of optimization variable as W, I'm sorry. I mean, everybody is used to thinking of it a different way. And we're going to take the optimization view here and stick with X as optimization variable. So from here on, except on slides that I forgot to change, we're always optimizing over X. Okay, good. But so this is a general. So far, I didn't say anything. I mean, this is a standard stochastic optimization or learning setup. But we want to talk about federated or distributed learning or optimization. And in particular, well, when doing that, there are a bunch of resources to worry about. So there's all the resources we worry about also when we talk about serial stochastic optimization, which there's lots of work on. In particular, the sample number of samples we need, and the compute or runtime, which are maybe the most significant. But we care about these distributed settings, in which, in addition to these resources, the other important resources are the number of machines or nodes or devices or what have you we're going to use, and significantly the communication, like how much we need to communicate. And also, when you talk about compute now, we have to be a bit careful. Are you counting kind of total computational steps, kind of the energy, or the latency, the wall time? And we'll see that many of these differ, but many of the approaches differ by which resources they emphasize. So in particular, the maybe most unique resource here is the communication. Okay, how many if we're going to orchestrate this optimization across a bunch of devices, how many bits of information are exchanged? And this was the focus of early work by Nina Balka and Avram Bloom, Shai Fein, and Yishai Mansour, that I think were the first that formulated a distributed optimization setting in a framework that can be analyzed can be analyzed. And I want to emphasize that there was work before, I think some of you will mention later, on showing methods for distributed optimization. But what I want to emphasize today is also analysis frameworks. And for me, for an analysis framework to be useful, it has to be specific and constrained enough that it can also show lower bounds in it, right? That I can actually argue kind of what's optimal in it, what's best. There has to be defined rules. Okay, so they define what they call the distributed PEC setup. This is not the notation they use, but this is kind of mapping their setup into the notation we're going to use here. I'm going to use here, and so. The way they thought about it, and I should say many of these bullet points are taken directly from Nina's slides that she generously shared with me, of the data being distributed across different locations. I can think of it as, in our language, of cross-silo, corresponding to kind of a cross-silo situation, where some of the distribution is in every location is access to a part of the distribution. This DM, right, the distribution on machine M, and we want to learn with respect to the mixture distribution across them. Okay? So you can think of taking the mixture, it's of course equivalent to taking the mixture here, the mixture of the distributions, or since by linearity of expectation, just the average of the objective on each machine. Okay? And the real kind of difficulty here is reaching consensus, reaching a single solution X that's good on for all of these machines, or at least on average. And the main resource that they talked about, so in order to reach consensus, right? If Katrina has some of the data, and John has some of the data, and I have some of the data, in order to get something that's good for all three of us, we're going to need to talk, right? We cannot do this without talking. And the main resource that they looked at is how much we need to talk, right? How much communication, and that's basically pretty much almost the only resource they really cared about here. So they viewed it in particular as a communication complexity problem. They mapped it to a formalized communication complexity problem. They did, I should say, I'm not going to talk about it here, they did talk also about issues already in 2012 about issues of privacy and okay, they talked a bit about incentives, but did have actually results also regarding privacy. But this is Nina's slide. The main thing was communication, and they were aware of privacy and incentive constraints. Okay, so what was their approach? So they analyzed mostly the realizable case. So in the realizable case, in a binary classification setting, you can just think of it as a hypothesis that is correct. All the data actually follows some hypothesis. More generally, you can think of it as just having take the loss to be non-negative almost everywhere, and that means the realizable case corresponds to the fact that there's a solution that actually has zero error, zero objective value. So in particular, that means that there's a single solution that's good for everybody, right? So Katrina has some of the data, John has some of the data, I have some of the data, but there's a single X star that's actually perfect both for Katrina and for John and for me. So this sounds at first like, okay, what's the problem? Just each one of us will work separately. If the optimum, Katrina has the optimum and John has the optimum, I have the same optimum, we'll just each optimize. But of course that doesn't work because there might be multiple, the difficulty is that each one of us might have multiple different zero-error solutions, but we need to talk to each other in order to find the one that actually works for all of us. Okay, so this is even, in this restrict setting, the problem is non-trivial. So one baseline here is that we just all collect enough data and send this, send the data between us. Yep.
Small question. Does the X star need to be unique, or can there be?
No, the X star does not need to be unique. So in general, it would not be unique. Okay. So you can think of it, something to have in mind is think of like a linear prediction, right? So that's there's a half space that's good for all of us. Sorry, I don't actually. I didn't include that picture. Maybe I should have. There's a half space that's good for all of us. Of course, each one of us has many half spaces that are good, right? But there's one that's good for all of us. But also there are many that are good for all of us. Okay. So the kind of baseline here, and it's important, I think, and we'll emphasize there to think about baselines, because in order for the analysis to be meaningful, we presumably want at the very least to be based better than kind of the most trivial baseline. The most trivial baseline here is just collect enough data to solve the problem statistically and send it all around. And each one of us, since we're only care about communication, once we did that, we can just all do it locally. Okay? And that requires communicating as many samples as we need for learning, which corresponds to the VC dimension divided by epsilon if you want to get an epsilon accurate solution. And Nina, Avram, Shai, and Ishai's main contribution was a generic method that is for any binary hypothesis class. So this is not some specific class, but it's a very generic method that allows reducing this communication complexity roughly from the VC dimension times 1 over epsilon to VC dimension times log 1 over epsilon. Okay? And this is done with log 1 over epsilon rounds of communication. Okay, so we have here an exponential improvement in terms of epsilon. Okay? And this is achieved with essentially optimal or close to optimal, so sample complexity. And computation is not like, in this general setting, when you're talking about general hypothesis class, we can't really talk about computation because it's not like depends on the hypothesis class. And the way they did this, which I think it's an interesting method that could be relevant also now, is essentially using a boosting approach. Right? So use a boosting approach to figure out which examples. So instead of Katrina sending me all her examples and John sending me all the examples, we're going to try to figure out which are the examples I really need from Katrina and John. Okay, so work like this. The method will work in rounds. We'll need roughly log 1 over epsilon rounds, and there's going to be one distinguished player, me. Okay, so this is important. There's one player here that's going to do all the work. Okay, so I volunteer, and in each round, each player is going to maintain some local distribution, rewriting distribution over examples. It's going to send me some small number of examples. Based on these small number of examples, I'm going to take these examples and what I've before and produce a hypothesis, a candidate hypothesis. And then, as in boosting, I mean, this is basically just an implementation of boosting. I'm now going to send this hypothesis back to everybody. Okay, so I'm going to and now John and Katrina got. I'm sorry, I keep picking on you. You're just are sitting in the front center. Each hypothesis, each of the nodes can now see, based on the hypothesis. So this hypothesis, they know exactly, all the hypotheses have so far. And what you want to do in boosting is reweight the example so that hypotheses that don't agree with the example are upweighted, and hypotheses that do agree with the example are downweighted. And each of the nodes, each of the players can do this independently, can reweight the distribution. Almost, we just need to normalize the overall weights, but that just requires sending kind of the sum of the weights from each player and exchanging that. So one round of broadcasting, and based on that, now each of the players can now send me back examples. So there's two kind of reweightings here. One is reweighting the different nodes, right? So I might want, if this hypothesis is also great for Katrina, but like really horrible from John, I'm going to want more examples from John. And the second is, John and Katrina themselves are going to send me more examples that are disagreeing with, are going to upweight the examples that are disagreeing with hypothesis I have so far and downweight the ones that I don't. Okay? And this way, overall, they're going to send me, instead of having to send me 1 over epsilon examples or VC over epsilon examples, the overall examples they're going to need to send me, they're going to focus just on these more problematic examples and reduce the number of examples they're going to send me to just VC times log 1 over epsilon. Okay? So this is, in some sense, you can think of it as a method of reducing communication by focusing and sending me just the important examples. And then the second, I want to note that the way I'm counting also communication here is not exactly in bits. So there are two resources. I'm both counting bits of because we're going to send these weights and that's going to be counted in bits. but also we're just sending hypotheses, right? So I count the number of examples of Z's. Sorry, I need to send. So I send examples. I need to send.
The hypotheses are defined implicitly.
In terms of implicitly, right? So in terms of the weights and the Z's, right? So the unit we're sending is the examples. Yeah. Question?
Yeah. What if there is no player that has connections?
Okay, so it's a good question. So at least in this talk, and both in their setting, at least in their main setting, and what I'm going to talk about, there's no connectivity issue. So it's an all-to-all connection, and so we just have one. The way they view it is everybody's connected to everybody. We pick one player, and that player is kind of the manager. Okay. You can map it to in a cross-device setting. There's a very naturally kind of a distinguished player, right? The server. They do both. Nina and co-authors talk a bit about over a graph, and we'll see later on. There's work by Ram and co-authors that more explicitly talk about what can you do when your connectivity is limited to a particular graph. But I'm actually intentionally not going to get into it in this talk. It's definitely an issue that I think. Okay, maybe I should say, and injecting also some biases. Separating between distributed optimization and federated learning, I don't know, it's again the same thing. It's this different regime. To me, one of the differences is when talking about distributed problem, I feel like the connectivity topology is very important, right? So people talk, for example, distributed optimization. You have sensor network, and you want to reach some consensus in sensor network, and then you have the topology is super important. In most applications I can at least think of, and I'm sure that many of you now can raise your hands and come up with a bunch of exceptions. In federated learning, to me, the topology is less important. The communication is, again, either server to devices or in a cross-silo setting where it's, there are different locations, but it's not, everybody can communicate with everybody. It's not like you really have physical connectivity issues. Okay, good. Okay, so the main advantage of this result is a very generic result. Like you can handle any hypothesis class. Just in terms of the VC dimension, which is the right parameter in some sense to capture learning. They also have some analysis for specific hypothesis classes that also take into account more specifically computation constraint and and for these hypothesis classes, this method is not optimal in general, but for the specific hypothesis they study. Then they do show that this is optimal. Now, whether the hypothesis classes are interesting or natural or not, I guess they can bring it up with Adam. So I'm just copying. But at least I would say that coming from kind of a call to computational learning perspective, these formulas, conjunctions, parities are at least well studied. Maybe Adam will agree with that. Good. We have Adam's approval. You like parities? Yeah. I don't like parities. They're a pain, but okay. They're good counterexamples. Okay. Good. They also go beyond supervised learning, and I think they have. I think in my mind, actually, this is the maybe the most interesting work here on clustering and PCA problems. So these are problems where now. I have some of the data, Katrina some of the, John some of the vectors, and we want to find a joint clustering of all our data, or even more interesting, we have a bunch of vectors and we want to find a subspace that will be low-dimensional subspace that will approximate well all of our data. And this is actually a hard problem. Again, they study it in this setting. And I emphasize that here the study is like in a worst-case sense, right? So I have some arbitrary data that's very different from Katrina and very different from John's, and yet we still want to find a subspace that's good for all of us. Okay, so what are the limitations of their approach? Well, one thing at least as presented, it's specific to binary classification. I don't think this is a very real restriction. The same ideas, at least, of boosting can be generalized more generally. What is a real restriction here is realizability. Okay, so they really rely because they use boosting relies very heavily on realizability. And the fact that we do have there exists an optimum that's an optimum both for me, for Katrina, and for John. And we just need to, we don't the fact that I'm need to satisfy also John and Katrina, I don't need to compromise. They should still be optimum. This is a huge restriction. They do have. I'm just going to flash a slide here without going over it in detail. They do have extensions to an agnostic setting, right, where we want to compete with the best we can do on average to all of us instead of the optimum. In these, if those are familiar, these results essentially rely on kind of like agnostic boosting results, and you have some. They based it on these results with Steve and Nina, and you can actually get something better with the more recent agnostic boosting. But without getting, do you want to ask about this slide? I'm in trouble. Yeah.
No, the guarantee seems weird. Error order opt.
Yeah. Okay.
That
Right.
seems dumb.
Okay.
I mean,
I would say weak. I don't know if dumb. Okay. Can you do better?
If I'm within a factor of 10 of optimal.
Okay. So right.
One optimal plus order
Right.
epsilon.
So what John is
It
complaining.
doesn't even make sense.
What John is rightfully complaining about is that the type of, so there are two problems with these extensions to the non-realizable case. Okay, let's actually talk about the second one first. This is completely non-tractable. So as opposed to the boosting approach, which, you have to still depend on the hypothesis class, but for reasonable hypothesis classes, it's very computationally tractable and very reasonable to implement. The agnostic boosting approaches, for those that are familiar with, are completely non-implementable, and the theoretical runtime is humongous, and they're also, I don't think anybody actually, probably somebody wrote code for it, but it's not like it's. And again, I've used these techniques also in my papers, and I always feel like this is feels wrong because this is just unimplementable methods. The second is, as John pointed out, what we really want is if there's some X star that's good and on average like 0.1 good for us, I want to be able to get error 0.1 plus epsilon. And instead, what they ensure is there's some constant C, okay, which is maybe 50, something like that. Okay, that's not very explicit. And what can ensure they get error 50. This constant cannot be, you cannot drive it to 1. It's like whatever comes from their method times the optimal error plus epsilon. Okay, so this epsilon, fine, we can get as close to that, but that means that if we have something with error 0.1, maybe the best we can do is error 5, and what's that good for, right? So this means that another way to view it is we are going beyond the realizable setting, because even if the constant is 50, if the error is 10 to negative 6, we're fine, right? We get 5 times 10 to negative 5. Okay, that's not so bad. Okay, so in some sense, what this means is it's not that you can handle a situation with any error, but we can at least handle a situation with there's some small enough error that we can handle. Okay, maybe that's a way that John is still making faces, but okay, that's what you get here. And I think that this is maybe a very significant limitation here. The other limitation of this, where is it? Of this approach is that the only resources concerning is communication. The computation actually, we don't save it all in compute versus a completely serial implementation. In fact, this is at the end, I'm doing all the work and I'm going to just do a completely straight up serial implementation. So I'm not using the fact that actually John and Katrina can also actually compute. Okay, so that's another issue here, but at least again, it's a well-defined question and a solution that is significantly improves over baseline, at least in a realizable case. As far as I know, the non-realizable, like what can you do in a non-realizable case, is still open here in this generic setting. I should say that this type of approach is also very similar, I briefly mentioned before, to a line of work by Nedic and Nedic, I think, and students, and many others as well, which didn't think about a learning setting, but just as a distributed consensus problem. Okay? And here, indeed, I'm kind of doing them disjustice, because most of the work here is actually about how does the connectivity graph, communication graph, affect things. Okay? But if we forget the connectivity graph, which is the main point in this line of work, then what we get back is essentially is something which is equivalent in some sense to the Balkan et al. Setting. Then again, we have each machine has a different local objective. So in Balkan setting, I mean, you can think of this local objective as an expectation over a different distribution. I mean, they just think of it as an objective that you can have arbitrary access to. But again, if we don't care about, if we're only counting communication and not number of samples, then it doesn't really matter. It's the same thing. And we want to minimize the average of all of these, so reach a consensus. And then here, most of the work is not in a realizable setting. And the work here is mostly like the number of vectors exchanged. And again, this is, I think, a weakness of this line of work, is that there's not a well-defined framework here in the sense that what is a vector exchange? I mean, I can compress everything I want into a single vector, but I don't know, multiplexing digits or something like that. And so there aren't, as far as I'm aware, in this line of work, actually, so it's not a framework in which you can get lower bounds because you can kind of cheat. And you can, instead of that, talk about bits maybe, but this is not generally done in this line of work as far as I'm aware. So there are methods, but not really, maybe not, it's not a framework that you can actually, the rules are not well defined here for this game. Okay, but mostly, what I want to emphasize, and here also the emphasis is mostly just in communication and not on computation, although all of the methods studied here are very easy computationally to implement. But the other main thing maybe that I want to emphasize, it's, I think, very different from this work from about 10 to 12 years ago by Raman et al. And Balkan et al., is what are we trying to do here? So where is the difficulty coming from, and what do we want to do? So in both of these, the main difficulty stems from the fact that we have very different distributions, very different objectives, and we want to try to reach consensus. And these, you know, the hard cases, the cases where I have to communicate a lot, are those cases where our objectives are going to be very different, or distributions are going to be very, very different. Okay? And I want to contrast that with a case that I find very interesting, and that I think is very relevant in federated learning. And actually, that is where I would at least start as a baseline. And that's an homogeneous case, where it's not that each one of us has a different distribution. Actually, all of us have access to the same distribution. Katrina as a button can get examples from the distribution. John can get examples from the same distribution. I can get examples from the same distribution. And in this case, we actually don't need to communicate at all. Okay, we don't need to be friends. Each one of us can work on our own, press the button as many times as we need, and learn independently. And the way that we, oh wow, how am I doing on time actually? Okay, the way that I, and really the goal here is to leverage the fact that we can communicate in order to do things better. So the fact that there are many nodes, many players, should only help us, as opposed to all this work on both Nina's framework and the distributed consensus. The more players, if now instead of just having the 3 of us, suddenly there's a room of 20 of us, the problem becomes harder. And it's like, oh my God, you know, there's a linear scaling there on the number of nodes. Whereas really, if we're just trying to work together to solve a problem, having more of us should just help us. There should completely reverse dependence on the number of machines. And I think this is the kind of main thing here. They want to try to do something collaboratively and reach consensus. And there has been work on trying to apply, some early work in distributed optimization, apply this distributed consensus problem as a primitive in order on the empirical objective. But again, any method that's based on that will necessarily have this like in reverse dependence on what we want in a number of machines, which just say things become harder when we have more machines, which is wrong. Okay? And something we maybe probably not get to later is even in the setting where where maybe we do have different distributions, I'd still argue the dependence should always be that if there's more of us, then things should be easier and not harder. And there are several ways to think about it. Well, one is maybe we're different, but hopefully we're not all that different. Otherwise, what's the point? We'll just like work separate. You know, we don't gain anything. There's nothing saying that we need consensus. In fact, if each of us has different distributions, right? So if my text is actually in Hebrew and John's text is in English and Katrina's text is in French or something like that, and there's like no connection between those languages, then there's no reason to reach a single predictor that's good for everything. I mean, each one of us can just have their own private predictor. Right? So you can think of the objective as not finding a single X hat that works for everybody, but this machine-specific X hat. And again, the hope is that by working collaboratively, we can leverage the similarities and work less, but rather than fight hard in the cases where we disagree. Okay, and in any case, the guiding principle is again having more nodes, more machines should only help us and not hurt us. And the other is we want to emphasize also computation, not just communication. So the framework that, okay, let me pick up pace a bit. So now, because otherwise I'm never going to finish. So in particular, to study computation, what I'm going to describe, so far I described this distributed pack learning due mostly to Nina Balkan and co-authors. I'm going to switch to talking about a different analysis framework, and I want to again emphasize analysis frameworks. And this analysis framework does address these concerns and also talks more directly about computation. In order to do that, okay, getting lower bounds in computation is impossible. Nobody can actually get lower bounds in computation. I mean, except for this ridiculously artificial problems, right? Or using complexity assumptions, but I don't know any complexity. That's too hard for me. Okay, so instead, what we're going to do is a surrogate. Well, Adam is maybe Adam can do that, but not me. So what we're going to use as a surrogate is what is a standard approach in convex optimization. We're going to, instead of counting computation, counting gradient accesses. We're going to allow accessing our function only with through a particular oracle accesses. And for now, at least, let's just look at first order oracle. And we're going to use the number of gradients we calculate as a surrogate for computation. At least we can now get lower bounds and say any method that's going to use gradients is going to have to do at least this many steps, so this amount of work. Okay, and okay, for now, this is. We'll get back to, I mean, the technical assumptions we're going to look at the next few slides. We're going to look at the smooth convex objectives with, over a bounded domain in Euclidean space. It's not so important because I'm not going to go over details so much. And this type of framework has been extremely successful in serial optimization, and we basically just know the answer, okay? And we know the answer in a very, pretty much any setup you can come up with, we know the answer, okay? So in particular, we know with the first order stochastic oracle, we know what the best you can do is, and more importantly, we know which method achieves it. Okay? And namely, that's just accelerated stochastic gradient descent. Okay? And this is a real thing. Like this, it's not just that theoretically this is kind of min-max optimal, but it really is a good method. And I want to emphasize this method was also a result of studying the analysis framework. So historically, people looked at gradient descent, okay? And then they tried to show, let's try to prove gradient descent is optimal. Okay, for non-smooth objectives, it is optimal. Try to prove it's optimal for non-smooth objectives, right? So it is important there's an analysis framework, you can prove lower bounds. Guess what? It's not optimal for smooth objectives. Okay, so this was, after years of trying to show that it is optimal, the Nesterov showed that actually it's not optimal. There's a better method, okay, namely acceleration, Nesterov acceleration, which is related to momentum. Okay, and this is really Nesterov acceleration is a direct result of thinking in terms of both upper bounds and lower bounds, and of the fact that you have an analysis framework in which the problem is well defined, the rules of the game are well defined, and you can think about lower bounds. Okay, so this is a serial case. We kind of know all the answers, and this is good for serial computers. The question is what happens, in a distributed setting. Okay, so the main analysis framework that we've at least been studying in the past few years is this distributed optimization with intermittent communication. Okay, so here can think of it as you think a bunch of servers in a cross-silo setting, and each machine can do sequentially gradient accesses. You can query any gradient access at any point, okay, but cannot communicate the k gradient accesses, and then there's a round of aggregation where everybody can communicate with everybody, right? And we're not counting here now how many bits you can communicate, but just how frequently you can communicate. Although again, all the methods, really the communication boils down to exchanging a vector or a few vectors, okay? And then, and this repeats in many rounds. So you have the parameters here of R rounds, k number of gradients per machine per round, and m machines. So this is in a kind of cross-silo or server setting, but you really have the same type of computation structure going on also in a cross-device setting, okay? So in cross-device federated learning, at least the way I think of it, describe it here, and this matches the description by Consini et al. And many others. We have a bunch of nodes, a bunch of devices, and each round we get a bunch of them, okay? And then each of those devices can execute some gradient oracles on its distribution. But again, we're thinking of this still as homogeneous, that all the the data is homogeneous across machines, and then send it back to the server. The server again samples a bunch of machines and so forth. So even though this looks very different, right? I have different machines operating at each round, and the communications all through the server. If you look in terms of the computational structure, it's the same computational structure in both cases. Okay, and we formalized this. This is work also with Adam, and again led mostly by Blake Woodworth, formalized this as in terms of a graph oracle model where you have oracle access to functions arranged in a communication structure defined by a graph. And this is one particular case of that. And this allows us studying both upper bounds and, importantly, lower bounds and understanding exactly what the optimal methods here. I should say, and maybe I'll go over it very quickly without actually, I'm going to flash some equations, but I'm going to have time to go over them, that the framework is the same in both the cross-device and in cross-silo, in the sense that it's the answer, the parameters here are the same parameters, number of machines m, number of rounds r, and number of gradients per round. What's different, and so once you know the answer, the min-max sample complexity for this, then you just know the answer. How do you use it how you use it and how you interpret it in different settings varies, because in particular, what's flexible and what's fixed is different in these settings. In the cross-silo setting, the number of machines, which is a number of servers, number of silos, number of hospitals is fixed. Right? We're doing a collaboration among 17 hospitals. We just have 17 hospitals. We can't now say, oh, actually, I need 19. You don't have 19. You just have 17. Okay. What you can change is how frequently you can communicate. Okay, we can, I would like to communicate as little as possible, as few rounds, but that's something flexible. And so really the question to ask, once we understand the min-max complexity, you can ask, what's the minimum? I think it's okay. I'm not going to go over I'm not going to explain you any of these equations because of time, but I can ask, what is the minimum I can communicate by still, being optimal? In the cross-device setting, the game is different. Okay, the number of devices now is flexible. Okay, I can use 1,000 devices per round. I can use 10,000. I can use 30,000 devices per round. That's flexible. The number of rounds I do is kind of fixed because I'm going to train for 5-6 days. I don't know, and that's as many rounds as I can do in those 5 days. Okay, but again, you can now ask, using the same math, you can ask a different question, which is, if I want to be, do the best I can over 5 days, how many devices do I need each time? Okay, how many devices again do I need to collect? Okay, so just okay. So what's the answer here? So first of all, we have to think of the baseline method. So one baseline method is mini batch gradient descent. In each round, don't take advantage of the local, no local updates. You just use all these gradients to compute, get a tight gradient estimate at a single point. Okay, so you just use all of these pink gradients to calculate a gradient at a single point. And so using effectively a k times m size mini batch, and then just do stochastic gradient descent with this mini batch. Okay, and we understand the analysis for this. And again, I'm not going to go over the equations here. You can think of them for now just as pictures. I'm going to talk about them instead of going over them because Ginger's going to kick me out in 5 minutes. But you can get some analysis, and this is what I consider a baseline method. You can do a bit better than that because we said before that SGD is actually not optimal. You can accelerate it. So you can talk about accelerated mini batch SGD. Okay, and this is one baseline. You can ask, is this the best you can do? Well, it's not always the best you can do. There's actually an even simpler baseline that sometimes is better than that. An even simpler baseline says, forget all the machines. Okay, I don't need Katrina and John. I'm just going to work on my own. Okay. And just run stochastic gradient descent, or again, accelerate stochastic gradient descent just on my examples. Okay, so that in some regimes, that actually better, right? So if I communicate very infrequently, okay, I'm doing many, many more updates, and this is actually better. Okay, the question is, can you beat these two baselines? Okay, for a method to be justifiable, it needs to beat these. And the main method that seems natural here, which is we already heard about yesterday's what I call local SGD or federated averaging, federated SGD. I mean, it goes by a bunch of names, but basically the idea is that I'm just going to try to take the best of both worlds. I will calculate, use all the machines, and instead of just calculating all the gradients at the same point, I will actually do local updates. And in the end, I'll average everything and again take another step. And there's been many attempts at analyzing local SGD, and when we started looking at it, it seemed that all of them are actually worse than the baselines. Okay, so you get a guarantee here, but the guarantee actually doesn't show any improvement about this much simpler method, which is mini batch SGD. So what's going on here? It turns out that you can actually improve in some regimes. So we have a slightly tighter analysis that shows that in some regime, actually, you can improve over mini batch SGD. Okay? But surprisingly, what we found is sometimes you can improve over mini batch SGD, but not always. And this first bothered us. It seemed like the analysis was wrong, and then we saw that no, this is true. we can show a lower bound on local SGD, and this lower bound is worse than the mini batch SGD upper bound in certain regimes. Okay? So it seems that the picture here is a bit more complicated. This method that you'd think would always improve, actually sometimes maybe is better, but sometimes is not. And you can see this empirically. So mini batch SGD is the green, local SGD is the blue line here. Frequently it's better, but in some parameter regimes, in particular, when we have a lot of machines and very few updates per machine, it's actually worse than mini batch SGD. It's actually even worse than something even stupider, which is using a single gradient per machine per iteration, which is even a stupider. Okay, so this is, again, our analysis of local SGD. You can actually improve this, again, by adding acceleration. So this is nice work by Yuan and Ma. And the question is, okay, so can you improve it further? Can you show benefit? And something to note is that even though local SGD does improve over mini batch SGD, it actually only improves over mini batch SGD in settings in which this single machine approach is dominant. So these guarantees for even accelerated local SGD do not improve over, they improve over one baseline, but do not improve over the combination of these two very simple baselines. Okay? And again, we're back in this situation. We cannot actually justify local SGD. The only case in which local SGD can show improvement over mini batch SGD is when there's an even simpler method that is better. Okay, so what's going on here? Can we really, does local SGD really not work? Well, let me skip this and just say that in one setting in which it does work is if your objectives are quadratic, then you can show that local SGD really is better, dominates both mini batch SGD and single machine, and is optimal. But then something even stranger happens, that all you need to do is local SGD with a single step of communication. You just need to do average at the end or one shot. Okay, and this would be optimal. Yes, John.
Why are we saying sigma on square root m is optimal if we have quadratic objectives? Because shouldn't it be sigma squared on m?
Sigma, it's not strongly convex. Wait, what's your problem?
No, so because we have quadratic, shouldn't we always be getting that worst sort of a one on k rate, or I don't know what, one on the number of iterations type of rate, one on sample size, because it's quadratic?
No, only if you're
even without strong, I mean, if you're not strongly convex.
Oh, okay,
if you're not strongly convex, then
so you are okay.
Anyway, right?
No, not if you're. No, you don't get, if you're noisy in a noisy quadratic not strongly convex, then you have.
I don't understand. How can you be in a noisy quadratic which is not strongly convex? Then there should be an interpolating solution, right?
Yeah. So no, why?
How do you? Maybe I'm being really.
The objective is quadratic.
Yeah.
But it's not. It's noisy, right? So it's not a deterministic objective. You have variance.
Yeah.
The variance doesn't go to zero when the. So okay, the important thing is the variance doesn't go. We're not in a realizable case. The variance doesn't go to zero when the optimum.
But then we're strongly convex, right?
No.
What if your population objective is quadratic, what direction do you have that's not strongly convex?
You can have degenerate
equally bad,
directions.
like two
Yeah.
equally bad optimal solutions.
You can have degenerate directions. You can have an entire subspace of solutions. You can have very, very slow spectral decay. So remember, these are dimension-independent bounds. So you can have arbitrary slow spectral decay. In the Hilbert space, you can have arbitrary.
I see.
Okay.
I see. So sorry. So we're just making the thing very poorly conditioned.
Yes.
Sorry.
Yes. Okay. Arbitrarily poorly conditioned.
My bad.
Okay. Okay. The point here is that for quadratics, we only need to do average at the end SGD. So that's actually kind of good news. We don't have to communicate at all, but that's just for the quadratic case. Okay. What happens in a non-quadratic case? So there, actually, something that I found even more surprising. It turns out you can show a lower bound here. That's not a coincidence. We could not improve over these two baselines because these two baselines are actually optimal. No method can improve over those two baselines. Okay. Okay. So what does this tell us? And I'm going to start wrapping up. So in this particular setting, we could kind of like analyze. We can get, you apply our analysis framework and just get the answer, right? This is kind of point one. We have a min-max. We know exactly what the complexity is, and we have an optimal method. Okay. And the optimal method is just doing mini batch SGD or single machine. One off mini batch SGD and single machine SGD. The question is this satisfying? So the answer to me is this is extremely not satisfying because this does not agree empirically with our observations that local SGD frequently improves over mini batch SGD. And also, by the way, in the quadratic setting, also the answer is not satisfying. Quadratic setting, we see that local SGD improves, but average at the end, just communicating once is optimal. But what we see empirically is that communicating many times, even in a quadratic setting, helps us. And to me, what this means is that we have to refine our analysis framework. We have to think a bit better about what are the conditions under which local SGD, we actually get improvement. Let me skip this. I also briefly want to mention here another setting we don't understand completely is heterogeneous setting. I don't have time to go over. We do have some upper bounds and some lower bounds. And the key thing here is how do you measure heterogeneity? And we do not, for any way of measuring heterogeneity, we do not know, for any reasonable way, we don't actually know the answer. We have some upper bounds, some lower bounds are actually tight, either with zero heterogeneity, meaning homogeneous. Well, not necessarily. Either zero heterogeneity for some measure of heterogeneity or arbitrarily bad heterogeneity, but for intermediate heterogeneity, we don't know actually the answer. And an even more interesting setting, we already talked about this a bit, even more interesting setting, which I think is completely understudied, and again, we don't have the answer, is this the real setting we're interested in which we have a population over machines, each with a different distribution, or each time we're sampling a random set of these. So this is kind of a partial participation setting. Again, we do not know the min-max rates here. Okay, let me summarize. What I showed you is, in the second part, is an analysis of one particular analysis framework in one particular setting. And I think in going forward, even in that, so in that setting, we kind of got a min-max answer, but we don't know if it's useful. But let's see what else we can go. So first of all, there are many analysis settings that are completely well defined, and I kind of skipped the slides here very quickly, but I could define them perfectly formally. And again, I completely set the rules. There is an answer. There is a min-max rate. There is an optimal algorithm. I would like to know what it is, and I think that's completely attainable. And that includes a homogeneous setting, partial participation setting, non-convex settings, or what I talked about is only for convex. We do have, we as a community, right, have upper and lower bounds for non-convex optimization. Again, non-convex serial optimization, we're actually getting a pretty good understanding of now. We do have actually, in some sense, we know the min-max answer, but non-convex distributed is completely open, and these huge gaps. And even more so for using higher order, if we talk about using higher order, this is all with gradients. We can also ask the same question. We have various higher order or other types of accesses that can improve here and are open. And incorporating other constraints that come more from system modeling. And another question I think is interesting, so far we talked only about counting rounds of communication, but not actually bits exchanged. And you can think of reducing rounds of communication as a way of reducing communication, but you can also reduce communication just by exchanging less bits. And there's a lot of work, a lot of it by Peter, also on using actually compression techniques for compressing the gradients, either with some unbiased estimate of the gradients or keeping the top k coordinates, including work with the error feedback framework that's both work for doing this compression more effectively, and especially for analyzing. This is open. But I think even more interesting than analyzing these specific methods is trying to think of what is the right analysis framework. We're clearly missing something here. The fact that we do not have any assumptions under which local SGD is actually better than mini-batch SGD, average at the end, or a single machine, which are all very kind of stupid baselines, says that we're really missing something here. We really don't understand what makes federated learning or distributed learning actually works. And we don't know how to measure heterogeneity. I mean, I think it's key. We do want to talk about heterogeneity, and we don't know what is the right quantitative measure to say how similar are two distributions. Okay? We have a bunch of different ways of doing it, and just by the fact that we have a bunch of different ways, you can already know that we don't know what the right way is. Okay? And also, what is the right, especially in a heterogeneous setting, what is the right objective we should care about? Should we really care about the average over the machines? I mean, why average over the specific machines we have? I don't think that's particularly interested. Maybe the worst case over some out of sample of other machines. There's a bunch of different objectives to talk about in a heterogeneous setting, and it's not clear which is the one we should care about. So this is, I think, the places where it's particularly interesting to think about both the application perspective, the system perspective, and the optimization perspective. Last note before already I'm over time, way over time. I'm sorry. But I think this is important. Another thing that I think I didn't have time to talk about, but I think is super important, is the heterogeneity not only of the data, but the interaction of the data heterogeneity with the I'd say machine heterogeneity. That's both hardware and communication and availability, reliability, and heterogeneity. And the fact that these two are not independent creates a lot of problems. So if the machine heterogeneity and the data heterogeneity were independent, right? So each machine had an independent communication delay and independent source of that would be fine. But the fact that machines which have particular hardware characteristics tend to have also correlated data. So for example, machines which are maybe older phones have to have that maybe certain languages are more prevalent in older phones rather than newer phones that have less reliable connections, can really create situations where you're starving out a significant portion of the population. So think about even a setting where you're each time using a bunch of machines, but they have varying delays and you don't have time to wait until the one with the longest delay. So you just take the first half of the machines that respond, right? If all your machines with a particular data characteristics are always late, you're just never going to see that data. And how to handle this while not complete. So the solution of saying, I'm just going to wait for everybody, that's going to slow down everybody and again, be unfair for machines that do have a lot of data. How to actually handle these situations is, I think, particularly challenging. So, okay, I think I can take the question after Ginger cuts me off, but thanks.
I'm going to get set up, but yeah,
Yeah,
go
sure.
ahead and any questions for, first of all. Any questions for Nati? Maybe one quick question?
Just a quick comment. For this different processing time, now we have Minimax.
Okay. Are you going to talk about it?
No, I'm not going to talk about
Okay.
So, you talked a little bit about the pack setting and then about the convex setting. Sorry?
Yeah.
So do you, a lot of these questions make sense in either of the settings? I mean, do you have a sense of as a community, we've certainly drifted more towards, I'm trying to understand continuous settings because they seem to be most relevant, say, to deep nets, but do you think trying to understand these questions in the pack setting, still has something to teach us?
Well, the short answer is yes. So I think that we shifted towards continuous for two reasons. One is because, well, that's what we're doing. I mean, we moved away from learning decision trees to learning neural nets.
Right.
And definitely nobody's learning conjunctions, right? And well, okay, except my students in my course. And the second thing is that there's something appealing that we can actually talk about. We have a good surrogate for runtime, whereas in the kind of Vapnik VC setting with abstract hypothesis classes, it's very difficult to actually talk about runtime. So because of those two reasons, I do think the right thing to look at is this setting. However, I do think we can learn a lot. So the boosting ideas, for example, that Nina, Misha, and Shai suggested, I think are very relevant. Boosting is definitely applicable also in a continuous setting. Okay? And so I do think we have a lot to learn from that and think about it in terms of thinking about things. But I do want to stay in the continuous setting.
This automatic framework doesn't allow us to reason about things like sugar regularization. There's a whole bunch of techniques which are not covered by the optimization framework, which you can do.
Wait, the continuous framework does allow us to reason about adding realization or not. So I skip that very quickly, but it does definitely allow us to talk about that. The answer, by the way, is that you don't gain by adding explicit. I mean, SGD already has in some sense regularization, right? But you don't gain in terms of the min-max rate by adding explicit regularization on top of that. But it definitely does allow us to consider that. Yeah, I think I mentioned it. Oh, it's not here. Yeah, so there were suggestions, I think actually by Ginger and co-authors, maybe also by you guys, of adding elastic terms, which are a form of explicit regularization in each outer step. But these things are provably don't help within these set of assumptions, right? So under other assumptions, maybe they do help. And it definitely falls within something that's
Okay, I think let's thank Nati again. right, so now we have a session of short talk.